Alright, so we're ready for our next video on limits for Math 1560, Calc 1 for the fall semester at the University of Lethbridge. In this video we're going to actually start getting into calculating limits using some of the algebraic properties that we talked about in the previous video. So these will be some of the examples where in order to work out what the value of a limit is, it's going to be necessary to do a certain amount of algebraic manipulation. In the first example, we'll show you one example where this is not necessary. Here's sort of a direct application of the limit laws. Let's suppose we want to evaluate this limit that we've got here. So remember that we had some rules saying things like the limit of a sum is sum of the limits, same thing works for products, quotients, things like that. And so the first thing we can see here is that we've got the limit of a quotient. And if we want to sort of break things down into steps, well, the first thing that we could do is we could say, well, that's the limit of the top. Okay, x going to 3 divided by the limit of the bottom, x going to 3. Make sure that you include that limit at each step, because if you, even if it feels annoying to write that limit every time, as soon as you drop that limit notation, that equals sign that you put there is going to be a lie. Now you can break things up. You can do the limit of the sum, top and bottom. We'll see how far I actually want to go with breaking things down here, but we could do the limit of x squared. We could even do, let me kind of do two steps here. One of the other limit laws says that you can pull out constants, so I can pull the 2 out of that limit there, so the limit of 2x, and then I've removed the 2 on the bottom. The limit as x goes to 3 of 5 minus the limit as x goes to 3 of x. And remember that the limit of x, as x approaches any value, you just plug that value in. So the limit as x approaches 3 of x is simply 3. Another rule said that if you have a square, you can always, once you've got the limit of x squared, you can move that square outside the limit if you want. So we could write that like this, limit of x, and then the whole thing squared. So now we know what we've got. We've got 3 squared plus 2 times 3 over 5 minus 3. And we can simplify that if we want. We've got 9 plus 6, we've got 15 over 2. And you probably notice that's exactly what you would have gotten if you had just plugged in x equals 3 at the beginning. And for a lot of functions, for a lot of limits, that's exactly what you do. You just plug in the value of x, which makes it seem like there's nothing all that special about limits. It seems like it's the same thing as just evaluating a function. But this turns out to only be true for certain well-behaved functions, what are called the continuous functions. We'll be defining continuity in a later video. But continuity is basically this property that you can evaluate a limit by just plugging in the x value. We'll see soon enough that that's not always the case. Now, the other thing you'll recall from the earlier videos is that when we're evaluating a limit, we're considering values of x that are close to a, but we never actually consider the value x equals a. We're near a, but we're not actually equal to a. And because of that, the limit really only cares about values of x that are near a point, not at the point. It means if I've got two functions that agree everywhere except at one point, their limits are going to agree, right? Even if the two functions are different, so we might have here, so even if it turns out that f of a is not equal to g of a, or even if one of these is undefined, right? So maybe one of these is not even defined at x equals a, or they are defined but they're not equal. That's okay. The limits will still agree as long as they're equal everywhere else. So to give you an example of this, if we were working with functions, right, if I considered the function, let's say f of x equals x squared minus 1 over x minus 1, and the function g of x equals x minus 1, sorry, x plus 1, okay? Now, these two functions are almost, but not quite the same. For the first one, I can factor the numerator. I can factor this as x minus 1. It's a difference of squares, x minus 1 times x plus 1. And on the bottom I've got x minus 1. Okay, so I can factor things out like that. And then I could look to cancel terms. I've got a common factor top and bottom. By the way, just as warning, right, there's people who are always tempted to kind of, they see x as top and bottom kind of at this stage here. There's nothing you can cancel at this stage until you factor. You're only ever allowed to cancel factors. You're never allowed to cancel terms. But now that I've got things factored, I can cancel this guy with that guy. Well, can I? This is almost always valid, but there's one point where this is not valid. This is not valid when x equals 1. So I have to put in this caveat here that x can't be equal to 1, because the original function f of x is not actually defined when x equals 1. If I put x equals 1 in, I get 0 divided by 0, which has no meaning, right? So these two functions, they agree at every single point except at x equals 1. And so it would be valid to say, and maybe I'll just kind of squeeze this in a box, what we can't say that the two functions agree at 1 because one of them is not defined. But what I can say is that the limit as x approaches 1 of f of x equals the limit as x approaches 1 of g of x, because they agree at every other point. And of course, the limit as x approaches 1 of g of x is easy. We plug in x equals 1 and we get 2. Alright, so let's see how this principle applies to a couple more examples. Alright, a lot of the first examples that you're going to do, the first exercises you're going to try, are these ones where you have rational functions. You've got one polynomial divided by another, and by the way, the first thing that you always try is you say, okay, can I plug in the value? Can I do a so-called direct substitution? And so we say, okay, what would I get? What would I get if I plug in 2 on the top? On top, I would get 2 squared is 4. 3 times 2 is 6. 4 plus 6 minus 10 is 0. And on the bottom, 2 squared is 4. 4 minus 4 is 0. So I would get this 0 over 0 limit. And whenever you see this 0 over 0 form like this, 0 divided by 0, this expression has no meaning, but it does tell you something. It tells you that you might yet be able to dig out an answer if you simplify further. And so what we do is we say, okay, let's go hunting for our answer. So why don't I see if I can factor, right? I know that if I plug a value into a polynomial and I get out a value of 0, that tells me there's a factor I can take out. And so let's see. I know that one of my factors must be x minus 2. The bottom I know how to factor. It's a difference of squares, x minus 2 times x plus 2. What's the other factor up top? Well, I need something that multiplies to give me 10. And I need a plus in the middle, so we must have to do x plus 5. And you can check that that does indeed work out. Now you've got this x minus 2, top and bottom. I can cancel it, and I can move on to here and say, okay, I've got x plus 5 over x plus 2, and this is justified by the previous theorem. So I don't have to say anything like, well, okay, this is true except when x is equal to 2, because if I'm considering a limit where x is approaching 2, I'm never letting x equal 2. So x equals 2 is not even a possibility, so I don't have to worry about it. That's the nice thing about limits. So now that I've simplified, I simply plug in x equals 2. 2 plus 5 on the top is 7, 2 plus 2 on the bottom is 4. Notice I've jumped right to the answer. I don't expect you to actually break things down in terms of those limit laws like we did in the first example in this video. Once you get the hang of it, you realize that, once you realize that you're allowed to plug in x, go ahead and just plug that value in, get your answer. Okay? Here's another one. This time we're dealing with radicals. There's a square root involved. So again, the first thing I ask is, okay, what if I do direct sub? So if I do direct sub, up top I get minus 1 plus 1, I get 0. On the bottom, what do I get? I get minus 1 plus the square root of minus 1 plus 2. Okay, well 2 minus 1, that's 1. The square root of 1 is 1. 1 minus 1, 0. So again, we see we get this 0 over 0 limit. This is our clue that we go searching to see if we can simplify and get a better answer. So how do I simplify this one? How do I simplify this limit? Okay. And again, notice I'm writing this limit sign on every step. Well, one of the tricks that you can use when you have a 0 over 0 limit involving radicals, if there's a square root involved, you can try rationalizing the denominator. So how does that work? Well, what you do is you take what you have to begin with, okay, and you multiply top and bottom, and the thing that you multiply by, you take what you had on the bottom, but you change the sign in front of the radical. So that x plus root x plus 2 becomes x minus root x plus 2. And anything that I do to the top, I must also do to the bottom. Anything I do to the bottom, I must also do to the top. And the reason that we do this is it sets up this sort of difference of squares thing. The cross terms, when I multiply out my binomials, when I do FOIL on the bottom, those cross terms actually completely cancel out. And what do I get? I'm going to leave the top factored for now. Because remember, we are expecting something to cancel out eventually. So what do I get? Well, x times x is going to give me x squared. Right? I get x squared. The cross terms cancel, and I get x squared minus, and then I have x plus 2. If I square a square root, that square root goes away. And what do I have here? Let me just kind of let's kind of grab this here and say, what do I have there? Well, first thing, that minus sign's outside the brackets. By the way, those brackets are crucial here. Very easy mistake to make is forget those brackets when you drop the square root, and then you lose a minus sign. I've got x squared minus x minus 2 once I push that minus sign through. That is x plus 1 times x minus 2. Well, that's good news. That's good news because now I can take that, I can put it in there, and what do I get? Well, let's throw that in, and after we throw it in, notice that I can cancel that guy and that guy. I'm running out of room, or I would write that step. Sorry, guys. There's only so much room on a tablet screen. So what have I got? X minus the square root of x plus 2 once I cancel that x plus 1 factor. And when I cancel it from the bottom, I've got x minus 2. And now I no longer get a 0 on the bottom, so I can plug in my x values. So I get minus 1, subtract the square root of minus 1 plus 2 over minus 1 minus 2. And what is that going to give me? Up top, I'm going to get minus 2. On the bottom, I get minus 3. Those two minuses cancel out, and I get 2/3 for my value. Okay. Before we wrap things up, let's just point out that things aren't always going to work out so nicely. Here's another limit where the first thing we do is we say, okay, direct substitution. What am I going to get? Well, up top I get 1 squared plus 1. I get 2. And on the bottom I get 1 squared minus 1. I get 0. So if we think about what happens as x is getting close to 1, well, the top is getting close to 2. The bottom is getting closer and closer and closer to 0. So we've got a number that's close to 2 that's being divided by successively smaller numbers. That means that the closer x gets to 1, the bigger this number is going to get. So we could maybe say something about the limit being infinite. We will talk about infinite limits in a later video, but the simplest thing we could do here is we could just kind of write something like this, right? We could say, I don't know, this is a bad way to do it. We shouldn't say 2 over 0, right? That's not a bad thing to do, good thing to do. So what we should say is simply that this limit does not exist. If you want to, you could give some reason, like the function is unbounded. meaning that it gets really, really big as you get close to 1, right? There's lots of ways that a limit could fail to exist, right? The limit could fail to exist because you've got a jump, like we've seen in earlier examples. It might be that it goes off to infinity. We'll see that there are even stranger ways sometimes that limits can fail to exist. But the reason we know this doesn't exist is we get that 0 on the bottom, but we don't get a corresponding 0 on the top. So the only time you bother trying to factor and cancel out that 0 is if you do see under direct substitution that both the top and the bottom are 0. That's your sign that you can go ahead and try to look for a limit. Okay, that's it for this one. In the next one, we're going to move on and talk about the squeeze theorem.